Okay, welcome back. So in our last video, we put together a couple of runs of logic in our connective component workbench. We put a timer, and it's being controlled by our system bits. Bit 0, when that's true, it's going to turn it on. Now, in order for me to test my program, I need to have a processor to connect to and actually download it and run it. Well, we have, within connective components workbenches, we have a simulator program. Now, to get this to work, we're going to be doing this by a sleight of hand, as it were, because this is all going to be done internally on my laptop, but I have to kind of make sure there's a few things set up. So the first thing I want to do is see where this little setup of the X is. What that does is that clears any fault that was on the processor and clears any memory that like a ghost. If you see this triangle here, it tells you there's something wrong, and it will tell you what the fault is. This simulator will actually generate faults if there's a problem with the program. Excuse me. Now, the other part is this IP address. So these micrologics communicate by different methods, but for the simulator, it's got to use the Ethernet equivalency. So we have our IP address, and this has been generated by the processor talking to the internal Ethernet card in the laptop. So if I were to click this down, you'll see I might have a couple of other choices. So I've got the gigabit killer 2600 gigabit Ethernet controller. If I wanted to, I could use 192.168.0.111, which is a MediaTek wireless LAN card. Again, that's within my laptop. And the last one is a 127.0.0.1 software loopback interface. If you have an older computer that, for example, the Ethernet doesn't work, you have to actually use a USB stick, then that software loop would probably be your fallback position. I like to use the one that the program has selected, so I'm not going to change that. But I need to take a note of that. I need to actually write down that number. So I'm going to do that. I'm going to go, okay, that's 169.254.169.79. Okay, got that. Great. Next important thing is turn the device on. Invalid configuration, check the IP configuration or try another one. It wasn't happy with that one. Okay, let's try this one. 192.168.0-11. So that other one must have been the last time I connected up to something and it remembered it. That's okay, we're all good. Click on that. I got a green light. It's happy. I have my power light on. I've got my network light flashing and saying it's communicating. Down here, I'm in program mode. Now, you can leave it in program mode, but if you do that, the program won't run. It'll just accept the new logic. So I'm going to put it in remote, which means I can download the program to it when I want, and then once it's finished, it'll ask me if I want to put it back into automatic. Okay, so I'm going to take that, and we have that up and running. I can set that aside. And if we look up at our top of our toolbar, you'll see that it's green. It means the thumbs up. We're running. However, I can't do anything with it yet because I have to download my program. My big, huge program is going to be downloaded. To do that, once I have this done, I can hit that button and go download. But right now, it's going to go, I don't know what you want to do, because we haven't told the program, the software, how to direct that project to be downloaded. So we're going to go back to our first page, and it doesn't look like much, but over here I want to draw your attention to the upper right hand corner where it says set up a connection path. You see a little pencil beside that. If I press connect, it's going to try to talk, but it doesn't know who it's talking to. So there's a couple different ways to do this, but you're going to end up going to the same place. So I'm going to show you up here. We can go to communications and configure drivers. Here it is. What this does, this allows me to create the path that I want from scratch for the software to direct our project to the processor. So right now I have a number of previous communication drivers established. One is an AB ETH-1, and then I got an ABETHIP-1 and 2, and I got a VP1. Notice that they're all running. So what I can do is, if they're taking up too many resources, I can actually highlight one and stop it. And I still have the other ones running. Everything's fine. If I select one, I can configure it. And what that does is it allows me to point to a particular device. So if I had written down that other number, I could type it in. Right now it says, oh, 192.168.0.1. Oh, that's right there. I'm going to go OK. So I've already got that configured. I don't have to create another one. If I wanted to create another one for whatever reason, you simply hit the drop down on available driver types. And these are all the different communication protocols that the software can set up to talk to different PLCs. In this particular case, we're using Ethernet, so you have two choices: Ethernet devices or this Ethernet with a spelling mistake /IP driver. That is not actually a typo. That's actually a registered trademark. When the N is capitalized, the letters IP change. Normally, Ethernet /IP stands for Ethernet over Internet Protocol. That's what all your computers do. Every time you surf the net, your phones, everybody uses Ethernet over Internet Protocol. But if you're using a PLC and you're talking to machines, this driver is the capital N changes the IP to Industrial Protocol. And the Industrial Protocol has higher priorities as to things like, well, if I'm going to sort my traffic control out, I think inputs and outputs are probably really important. Safety is probably important. It just sets up the priorities a little bit differently than the Internet Protocol. For other devices that do not work on the Industrial Protocol, but you still want to communicate it, then you would just use the Ethernet devices. In this case, because it's all internal, either one will work. So I'm going to close this. We've already got a driver configured. Everything's good, except I don't have a path yet. Okay, now I have to use the pencil. So I'm going to click on the pencil, and I'm going to go to Browse. Now those drivers that I've set up, you'll see that each of them have their own little network. They've also added a USB because the software says, well, if you're talking to a micro, you can have it hooked up in USB, so I'll give you that option. The little plus signs allow me to open up and look at and scan that network. So I'm going to take, let's go to the first one. And I see the icons of 4 processors. Oh, 5, and one just got X'd out, and then, what happened there? Okay. At a previous time, I was talking to these 4 processors at some point in the past, plus this unrecognizable device, 14255, 14553. With Allen Bradley software, if you're talking to a device that it does not recognize, it'll still let you communicate. It just won't give you an icon. They used to have what they called electronic data sheets. It was a small file that you would add to the project. And once it had that, it would know all the handshaking, all the communications, how much memory was going to be involved, how much I/O was involved, all the pertinent details about that particular device was then loaded into the project. And also there was an icon file that would look like the device that they wanted to, and it would then appear in this browser. So in this case here, we have our 192.168.0.1. It's a Micrologix 2080 LLC50 48Q WBS, and it's probably our simulator. So I'm going to say, well, I can see it. It's not red X, because a red X means I can't find it. It used to be there, but it's gone. So I'm going to highlight it, and down at the bottom, our button shows OK. So it has said, yep, it's still there, and I can communicate. So I'm going to hit OK. I don't require this, so I'm going to clear this. Now, before I clear this, if you happen to see that particular IP address populate here, you can double click on it, and it will save you a step. So we've got that. Now I've already got a path. Notice how my path appears up here. That's my computer, that's the Ethernet port, that's my actual Ethernet address, that's who I'm going to talk to. So now I can press my download button. And when it does the download, the first thing the program will do is it will try to build the logic. It's going to look at the logic and make sure there are no mistakes. It will not allow you to put self-destructive faulting logic into the processor. It's trying to save itself some grief and save yourself some trouble, and it builds it, tests it, and if there's problems, it'll have down here failed, and you'll have little red X's that, yeah, thank you very much for trying. We have some lovely parting gifts called try again. Once we are successful in our build, you will get two choices: download or download with project values. In another video, we're going to look at project values, but in this case, we're just going to put download. And some actions going on. And then it asks us, it's now complete. Do you want to change to remote run to execute the progress? Yes, please. Nothing's happening. It's boring. Oh, the screen has changed. So now we have our two runs. The background has gone to this buttercream color, and everything is blue except our elapsed time, which says it's in red and it says 0. So this is where a simulator will help us out. So I need to have DI03. If I click on that, that's like me physically pushing the button, or in this case, because it's a stop button, I'm saying it's wired up. And then I'm going to take my automatic, because it's a retentive switch. I push my automatic push button in, and now I've got these two. So I'm just going to toggle this really quickly off and on, and it set my system bit, it sealed itself in, and I de-energize it instantaneously, and now my counter, or my timer, pardon me, is actually timing. And the actual value, my elapsed time, is being shown on the right-hand side, and the program value is on the left-hand side. So now that it's all done, it looks like I've done a really good job. I'm going to de-energize my cycle stop. And what we've seen has happened is, not only did I lose my system bits, once the system bit 0 went to 0, went false or turned off, my timer went false, and I lost my time. It's gone. One shot deal. So let's re-energize this, quick toggle, and now it's starting to count again. Notice it does it in milliseconds, and notice how it seems to be jumping. It's not like you're seeing 9, 10, 11, 12. It's kind of jumping all over the place. The scan time on these processors are very, very fast. By the time the scan sends its information and it gets to the PC from the PLC, and Windows has had its time with it, you're looking, as far as the processor and process is concerned, you're looking at ancient history. Okay, so this is now set our 15 seconds. So let's take a look at this, and I want to move this out of the way for a second. Now that we've done that, before I was able to look at and select a variable. I'm going to right click on this, and I have variable monitoring. Okay, let's take a look and see what happens when I do that. So that opens up a new box, and what it's doing is it's examining and looking at the values that are going on with our timer, which doesn't seem like in this particular case very much, because it just has ton my first timer. Okay, that's great. There's that arrow. Let's drop on that and see what happens. And now it tells me everything I need to know about what's going on with that particular timer. So my input is still true. You see the check mark there. My program time, that was set up before, so it's red. I can't change that. My Q is now got an active check mark, which means my output is true. And this other one called rising edge, or reg, it is also true. So this rising edge means that it has seen the input go from low to high. And once it's done that, that starts to, it's true as long as the input is true. Okay, so I'm going to go and say I'm happy with that. And I'm going to close that. And I'm going to toggle my bit again. And I'm going to toggle, I need to toggle number 0. Starting to count. And I'm going to go to here, variable monitoring. Oh, because I'm looking at the wrong thing. Ton. Okay, maybe I can do this again. I want to see that actually counting, so I'm going to go back to my simulator. Hopefully it'll let me do that. There we go. And we can see that we even have this P date changing, and you're seeing the timer count. Register, and once that's done, my Q turned on. And that's pretty much all you require for a timer as far as everything else that it's doing. Now, if I want, I have the ability, let's scooch as far as over I can. If I want to add a comment on an instruction that's particular to that instruction, there is actually a column that will allow you to do that in the variable selector. So I'm going to cancel this, close it, and I'm going to go up to here where it says connected. With Connected Components Workbench, with the free software that's available, this particular program will not allow you to make program changes on the fly. So what I'm going to do is I'm going to click on that, and it's going to disconnect it. I'm no longer talking to the processor. Now what I'm going to do is I'm going to add some logic that will make this timer repeat itself and turn on an output, and then we can watch this output down here on the bottom. Even though I may be in program mode, the program is still going to run. So let's do that. So I'm going to go here to my output and my Q. I want to show you two things. I'm going to add a run logic just for a moment. And I want to go to bit. Now notice on the next rung I'm trying to put a second output and it just says no. No, you can't do that. At least I can't do that in series. I can do that in parallel. So I put a branch here, and when you're doing branched outputs, it's a bit of a trick. You drop it on the rung first, then go to your output, drag it over and insert it inside. Then it moves the branch. I didn't write the software, that's just the way it works. Now, if I want, I can put a second output. I can put as many outputs as I want. But you can't put outputs in series, except if it's a timer or a counter or a special instruction. That cue is the same as a coil. That cue, when the timer's done, goes high, just as our system bit 0 went high when this was true, or if my one single contact here, these both would come on. So this is the exception to the no serial outputs. This output is a conditional output. This one will not turn on, at the end of our run, will not turn on unless this cue is made. So let's give that an address, and I'm going to go, notice how my outputs pop up first. I'm just going to take the first one because, well, it's a demonstration and I'm lazy. And I'm going to take this third rung and I'm going to avoid confusion. I'm going to go turn that off. And to make sure that this is going to work, I'm going to do two things. I'm going to change my time down to a lowly 3-second timer. I'll highlight that. I still have my hashtag. That's all good. So after 3 seconds, that's going to be complete. Now this is a output that is expressed as a set of contacts. So even though it is an output like this direct coil, in fact it's acting more just like a direct contact. So I can actually fool this timer. I'm going to grab a reverse contact or examine if open. So if this is off, then the rung is true. And I'm going to go TON_1 dot Q. So what I've just basically done is said when my timer is not finished, time. But if I'm finished, stop. And when it stops, it's not timing, which then means start timing again. And then when it's finished, stop. And then start timing again. So this is going to cycle itself. We used to call these a free running timer, and there was lots of applications for it when you wanted a heartbeat, when you wanted a flash, or something along those lines. So now that I've done that, I'm going to go up to here, and I don't want to be embarrassed and see that mistake. So I'm going to go up to the device on the top, and I'm going to go, please build my program so that nobody will see the little red circles in case I made a mistake. Yes, my build is successful. Awesome. So I did my job. And I'm going to go back up here to my top. I'm going to go download. Little drum roll. And it says, okay, you've already built it. Project's up to date. Perfect. It succeeded. No problem at all. So let's go download. Download's complete. Yes, please turn it onto run, remote run. And I'm going to go here so I can see that. There's my logic. Nothing's happening. Notice that my TON1Q, the reverse contact, is in red because the timer is not energized, and it says I'm true if there's no energy, if I'm turned off. Okay, so what I'm going to do is I'm going to hit this, toggle that, boom. That's closed that. Now my timer is not done yet, and this is going to flash so quick you won't even notice it. So this output should come on. What's wrong with my logic? What's happening is this output is on so briefly that the output never gets energized. That's not what I wanted. That's not good. I'm gonna fix that. Okay, I'm gonna disconnect. I'm gonna have to play some fancy pants here. I'm gonna make this, I'm gonna change this from a regular contact to a latch. Now I can go up to the top and hit set reset, or since that's highlighted, I can press my space bar. That's now a reverse coil. If I left it alone that way, then while the timer was not finished, it would be true, when it's finished it would be off. But again, I still wouldn't see that. So I'm going to make that a set. And then I'm going to grab a contact and another contact. This should work. I'm crossing my fingers, otherwise I'll be embarrassed. And I'm going to do a reset. And the reset's going to be the same as my set. And in order for that to set, I've got to be already set once. And then my qubit has to be set again. So when that finishes, it'll set that. And then the cycle push button, oh, I've got the wrong address here. I don't want cycle, that's a digital input. Silly rabbit, I want the digital input. See, even embarrassed myself. Digital output 0. So that already had to be set once. And then the next time the timer is true, so I'm going to go ton_1.q. So when that's set again, then that should hit the reset and turn it off. Then the next time it should turn on, and then that should be fine. Okay, I hope I got this right. Download build succeeded, yay. Now before, when we would make these free running timers, you only had two choices of time, milliseconds or seconds. And this worked flawlessly. But because this only has the millisecond base, it can go so fast it doesn't actually do anything, and we just get frustrated. So I'm going to call up my simulator again. I'm going to double click that really fast. And let's see what happens if I corrected my problem after 3 seconds. Oh, my set is on. So my output's on, but it's not turning off. Huh. Oh, I made the same mistake I had my push button again. I had to push my push button to reset that. Now one thing, I'm going to stop this for a second here. One thing I want to point out, when you're using the set and reset, it doesn't behave like a normal output in that if it's set, the reset is also highlighted. So there's not something quite right in the state, Denmark. I don't want that. I wanted the digital output. I thought I changed it. Digital output. My first timer. That's the digital output. Okay. Now when that's true, that's going to be true, but I have to wait for the timer. The timer's so fast it should now work. Crossing our fingers. When we put it in the download mode, it turned the output off, because every time it goes to download, it cannot download and operate the outputs at the same time. That would be unsafe. So whenever it goes in to download the program, it goes to program mode, turns off all the outputs, accepts the new program, and you put it into remote run mode, then you're allowed to actually go ahead and do the program. So I'm going to do that quick toggle. Timer's counting. Let's look at our output. Huh. It's still not working. Well, the problem we have now is that the logic gets solved so quickly it resets itself. Oh boy, I'm embarrassed. We did this all the time in the olden-fashioned days. Back to the drawing board. Well, there's a couple ways we can do this. We want a timer to flash and pulse, so I have a flasher. Now, in our toolbox of programs, we actually have one that does that. It's called a TONOV, a time on and then off, and is specifically designed to do what I'm trying to do, which is to make a flasher. There's another way we can do this, and what I want to do is I'm going to take this branch, highlight it. Now when you delete a branch, be careful where you highlight it, beginning or end. Take the end and go press the delete key. Poof, there it is gone. I'm going to go back and make this an output. There it is, the standard direct coil. And I'm going to play Mr. Smarty Pants again because I'm convinced I don't want to embarrass myself too much. Too late. Put a second timer. And this timer, I'm going to take that out. So when that's true, this timer is running. When this timer is running, I don't want this one running. So this one has to be done and start the time doing that. So I'm going to go to that. I'm going to put this in front of that and this in front of that. And TON_2 Q is not done. Go ahead. So that's going to go first and start the time. And this one, I only want this to start when TON_1.Q. And I want that to be when it's done. Oops, I just pressed the space bar. So, system's on. This is going to count because that's not done. It'll count for 3 seconds. When it's finished, this bit will be set. This will turn on this timer, which makes this one false. Oh no, that's not going to work either because that's going to time. As soon as that becomes not done, it'll still time. Then this will start timing. Yeah, that might work. Okay, let's try that. So then when all this is finished, I want my output to be on when my timer 1 is enabled. I think I've got the right idea. Now I'm going through all this because I want to show you some of the logic process that you start going through, and you make mistakes. You think it works and it doesn't, and then you say, okay, I should have just used that other timer. I'm trying to be smarty pants and do the tried and true. But let's try this anyway. Do, 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 do. Yes, please. And go back to our simulator. Toggle a bit. Away it goes. Okay, so it's timing. And it's not working. It's not done. My first timer gets clicked on, but it resets. Huh. Okay, you know what? All that hard work, and I've proven that this doesn't work. Okay. Alright, I'll do it the other way. I'm going to go disconnect this, simplify my logic by getting rid of this, and this, and this, and this, and go to our friend in our timers Mr. Tanav. Now notice that the instruction has changed. I still have my in, that's a bool. I still have my out, that's another bool. I've got my program time, and I have my elapsed time. Huh. But I got this PT0F. So let's put in this time, we know this one. Make it cap lock so you can see it. S. Nope, I gotta put 3S. I don't have to program that. This is how long do I want it to stay off? And I'm gonna put this not qubit in front. Now you're probably saying, well, why? You've got a programmed on time, you've got a program off time, why would you want that? The way a Tanav works, it actually is two different instructions. It's an on delay timer and an off delay timer. And off delay timers need to be kick-started. So let's build it, see if I made any goofy mistakes other than poor logic. Successful. Download. Go ahead. Yes, please. And we'll toggle this. And you notice it was on for 1 second, and then it reset itself. Now I can adjust these times so I can make it stay on longer, or have it come on quickly and then stay on longer and then turn off quickly. So this gives you an advantage. When we used to use the free running timers, if I wanted a flashing light and I wanted it to be on for 2 seconds, off for 2 seconds, on for 2 seconds, off for 2 seconds, then I would just change it to a 2-second free running timer and it would work. In this case here, I can have it so that I can do that, or I can say, oh, I want it on for 5 seconds, but off for a second, then 5 seconds, and then 5 seconds. I can adjust that. So if you're using a common horn or you're using a common light, this is a lot easier to work with, and it allows you to say, okay, under this condition, I want a long horn with a short beat, I want another long horn with a short beat, and that pattern, everybody in the plant will know it's a fire, or everybody in the plant knows that this machine's starting up, or it's a particular sound that's distinctive. Same thing with a pilot light or a siren alarm or any kind of annunciation. Or you just might want to have a motor just kind of jog in pulses. Not the most efficient way to use a motor, but in theory, like if you had a very small conveyor, you could set the contact to close the contact and then stop and open the contact, etc. So that is our timer and our on delay, off delay, or Mr., as I like to call him, Comrade Tanav, does the both. I want to change one other thing and bring it to your attention, and that is when it comes to timers and counters, it's the use of this part here where it says T#3S, and that'll be in the next video.